Today we're going to be learning about the reciprocal or rational parent function. So this is the last parent function that we'll talk about this year in Algebra 2. It is by some books called the reciprocal parent function, but by others it's called rational. We will probably use rational more often than reciprocal, but I wanted you to see both. So the rational or reciprocal parent function is y equals 1 over x. So I have only put in two x values here because, let's talk. If you plug in anything other than 1 here, like 2, 3, 4, anything like that, you're going to have a fraction to plot, and we don't want to have to do that. So if you plug in -1 for x here, you would get 1 over -1, which 1 over -1 is -1. Also, notice I skipped 0. Think about why. If you put 0 in the denominator of a fraction, that is called undefined. So we will not be using the x value of 0 because 0 cannot go in the denominator of a fraction. So actually that brings us to something very special about the rational or reciprocal parent function. Since you cannot have an x value of 0, that produces an asymptote on the y-axis. Why does that produce an asymptote on the y-axis? Because every single point on the y-axis has an x value of 0. Okay, and we cannot have an x value of 0 because 0 would make this fraction undefined. So the rational or reciprocal parent function has an asymptote on the y-axis. Okay, and then I also want you to think about plugging in +1. If you plug in +1, 1 divided by +1 would be +1. So my 2 points for this graph are -1, -1, and 1, +1. Okay, so I also want you to think about a couple other things. This graph will also never come out as 0. What I mean by that is there's no input that you can plug in here for x that will produce 0. The only way that a fraction can equal 0 is if 0 is on top, right? 0 divided by something is 0. Okay, there's absolutely no number that you can plug in here for x that will produce 0. There's no way this will ever equal 0. So you will never have a y value of 0 for this graph either, which is also makes this graph very special because then if y can also never equal 0, then you will have an asymptote on the x-axis because every single one of these dots on the x-axis has a y value of 0. So the rational or reciprocal parent function is a very special graph because it has two asymptotes. It has an asymptote on the x-axis and on the y-axis. So I also want you to think about what this graph is doing. So we have these 2 points, but what exactly are they doing? Well, if you think about continuing to plug in these positive x values, if you plug in 2, like I had stated earlier, if you plug in 2 for x, that would be 1/2. If you plug in 3 for x, your y value would be 1/3. If you plug in 4 for x, your y value would be 1/4. You can see that this graph on this side is going to hug this asymptote forever and always because it's just every single time your x value gets larger, your fraction is getting smaller and it's getting closer and closer and closer to this asymptote here, but it'll never touch because, like I said before, there's no way that no matter what kind of number I put here, there's no way that my y value that I get out will be 0. Pretty cool, huh? So also what I want you to think about is if you go back this way, if you go backwards, like if you plug in 1/2 for x, if you plug in 1 over 1/2, remember you would keep it, change it, flip it. So it'd be like 1 times, and you'd flip the half, and it'd be 2 over 1. So actually, these are going to grow and get kind of larger and larger y values. So this graph is going to hug on this side, and this part of the graph is going to hug on this side. And it's a similar thing here. If you keep on plugging in more and more negative values, like -2, -3, -4, that's going to be -1/2, -1/3, -1/4. So again, on this side, I'm going to hug and hug and hug and hug. And then on this side, I'm going to hug and hug and hug and hug. So that is what our rational or reciprocal parent function looks like. Okay, so that's what it looks like. Let's talk about the attributes. So first of all, the asymptotes. So we have a vertical asymptote. Trying to decide if I want to use a different color. Yeah, I guess I'll use a different color. So I have a vertical asymptote, which means up and down. I have a vertical asymptote at x equals 0. I have a horizontal asymptote, so vertical asymptote, horizontal asymptote, a horizontal asymptote at y equals 0. Okay, my domain is interesting as well as my range. So let's talk domain first. Left to right. This graph is going to go to the left forever, and then it's going to continue to hug and 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 get as far right as it can, but it will never touch this x value of 0. Likewise here, it's going to get real close to the x value of 0 as it hugs on the left here, and it'll go all the way right forever. So this graph will go all the way left forever, it'll go all the way right forever, but it will never, ever, ever use the x value of 0 because of this asymptote here. So how we say that in set notation is x such that x is an element of all the reals except x cannot equal 0. It uses every single other x value except 0. Okay, so that's the domain in set notation. Now interval notation is a bit different. So interval notation, we say the graph goes from negative infinity to 0, not including 0, so parentheses, union with 0 to infinity. So this means it goes from negative infinity to 0. You notice I use the parentheses because it will never touch 0. And then that's saying like union with, I had a break in between here. Okay, and then on this side it goes from 0 but doesn't use 0 all the way to positive infinity. So that's your set notation, or interval notation, excuse me. The range is very, very similar. It goes down forever, it goes up forever, but it hugs and hugs and hugs the y value of 0 but never uses it because the asymptote. So you would say y such that y is an element of all reals except y can never equal 0. And then same for the interval notation for range. So it goes down to negative infinity, up to 0, but doesn't touch. And then union with, it goes 0 on this one here, this graph here, all the way to positive infinity. Okay, so those are my attributes. So let's talk about moving this special graph. Okay, y equals 1 over x minus 5. The minus 5 is kind of a tail. It's on the outside of the 1 over x. So as you would imagine, as we've done in the past, that's a down 5 movement. So the minus 5 there means down 5. So I'm going to pick up my origin, move it 1, 2, 3, 4, 5 down. I'm going to put my new origin there, and as soon as you put that new origin, you should put your asymptotes. You're going to have an asymptote on your new x as well as your new y. Now in this case, the y didn't change, like the y values did change. They went down 5, but what I mean is the asymptote on the y-axis didn't change because I didn't shift left or right. So as soon as you draw that new origin, I want you to go ahead and plot your asymptotes. Okay, so you're going to, once you move your origin down, you're going to plot your points, -1, -1, 1, +1, and draw your curves, hugging the asymptotes. Make sure you've got arrows on both ends showing that it's going to go on forever. Okay, so there's my graph, and now let's talk about my information. So I have a vertical asymptote still at x equals 0. Like I said, that one didn't change, but my horizontal asymptote went ahead and it shifted down 5, so it's now y equals -5. So notice that affects your horizontal asymptote. Okay, this didn't change, so therefore my vertical asymptote didn't change. And then the domain and range would be very similar to what I set up here, except for, you know, the movement that we went down, but I really don't have time to discuss all that. So let's talk about shifts on this one. That -2 is inside the fraction with the x. So remember, inside the function with the x is going to be your horizontal movement. So that graph shifts right, as you might imagine, it's opposite of intuition, right 2. So I'm going to move my origin right 2, and like I said before, you want to go ahead and right away you want to draw those asymptotes. Okay, I don't have a stretch or a shrink or a reflect or anything like that, so I'm going to plot my original parent function points as is. So -1, -1, 1, 1, draw my curves to hug the asymptotes. Okay, and again, if you're thinking about the asymptotes, my vertical VA is now x equals 2, notice, okay, and my horizontal asymptote is still y equals 0, okay? All right, let's look at this next graph. So here we have a right 1 up 3, right 1 up 1, 2, 3. Right away I'm plotting those asymptotes, okay? And then you noticed right 1 up 3, that negative in front of the 1 in the numerator of the fraction. That negative makes the graph, as you might imagine, as we've been doing all year, reflect over x. So you need to take your original x and y values, which were -1, -1, and 1, 1, and you are going to multiply your y values by -1. So this will become +1, and this will become -1. So my new points will be from my new origin, -1, 1, and 1, -1. Okay, draw your curves. And then I have a vertical asymptote at x equals 1, and I had a HA horizontal asymptote at y equals 3. So notice the horizontal asymptote stays the same as this value, but again, my vertical asymptote opposite of that value. So one more that I want to get through with you. So here, this graph moves left 2, down 4, left 1, 2, down 1, 2, 3, 4. Right away, I'm going to plot my asymptotes. Okay, and then before I plot my points, I notice, look, that value is no longer 1. I have a 3. So that 3 is going to vertically stretch my graph by 3. So as you might imagine, again, you need to take your x and y values, okay, which were -1, -1, 1, 1, and you multiply your y values by 3, so -3, +3. Okay, so left 1, down 3, right 1, up 3, and the curve gets a little bit further away from the new origin, as you can kind of see. So, but it's still going to hug the asymptotes forever. Okay, so your vertical asymptote for this graph is x equals -2, and your horizontal asymptote for this graph is y equals -4.